Hello everyone, welcome to our channel Technical Academy. In this presentation we are going to study about the temperature dependence parameters of the p-n junction diode characteristic with derivation. So we will particularly focus on the mathematical part and we will derive the equation for the reverse saturation current, that how the reverse saturation current is going to vary with the temperature, and then we will see how the voltage is going to vary with the temperature. So let us start our presentation. The temperature variation may be calculated using the diode current equation, where the current is contained implicitly in the voltage Vt, that is thermal voltage, and also in the reverse saturation current. So the dependence of the I naught, that is reverse saturation current, on the temperature can be explained through the equation I naught is equals to K into T to the power m exponential to the power minus Vg naught upon eta into Vt. This is our equation number 1, where the meaning of K is a constant. This is our constant value, and I naught is the reverse saturation current, and EVG naught, where E is the magnitude of the electronic charge and Vg naught is the forbidden gap energy in the joules. So this total term will be the forbidden gap energy in joules. So for the germanium, here eta, this is our ideality factor. The ideality factor is equals to 1 and m is equals to 2, and Vg naught is equals to 0.785 volt. And for the silicon, eta is equals to 2, m is equals to 1.5, and Vg naught is equals to 1.21 volt. So taking the logarithmic derivatives of equation number 1, so this is our equation number 1. We are going to take the logarithmic derivative of this equation, then we will obtain equation number 2. So if you will solve this derivative of equation number 1, then you are going to get equation number 2. So here we have taken derivative of every terms, so we will get equation number 2. At the room temperature, we deduce equation number 2, that dln I naught upon dt is equals to 0.08 per degree centigrade. So it is going to fade, or it is going to decrease 0.08 per degree centigrade. This is for the germanium. This is for the germanium, and 0.11 per degree centigrade for germanium. So from equation number 2, from the experimental data, we find that the reverse saturation current increases approximately 7% per degree centigrade for both silicon and germanium, and since the value of 1.07 to the power 10 will be nearly equals to 2, so here we are assuming one value, that is 1.07 to the power 10. That means it will be equivalent to 2. So from this solution we can conclude that the reverse saturation current approximately doubles for the every 10 degrees Celsius rise in the temperature. So as we are increasing the temperature, if we have increased 10 degrees centigrade, then the reverse saturation current is going to double. Now from the diode equation, from the diode current equation, I is equals to I naught into e to the power minus b upon eta into Vt. So here it will be minus 1. I have neglected this part. From the equation number A, dropping the unity in comparison to the exponential, we found for the current, constant current, here the current is constant, so we have taken derivative of this equation with respect to temperature. So we got a new equation, that is dV upon dt is equals to V minus Vg naught plus Mn into Vt upon T. So this is our equation number 3, This is our equation number 3. So now consider one example to prove that how the temperature, how the voltage is going to vary with the temperature. So consider the example. Suppose that consider a diode operating at room temperature 300 Kelvin and just beyond the threshold voltage Vt, say at 0.2 volt for the germanium and 0.76 for the silicon. So if you will substitute these values, so here we have to assume we have to take one voltage that will be greater than 0.2 volt for the germanium, and for silicon we will take more than 0.76. Then after substituting these values in equation number 3, we will obtain that the voltage dV upon dt is going to change as minus 2.1 millivolt per degree centigrade for the germanium. So the voltage is going to decrease by 2.1 millivolt per degree centigrade rise in the temperature, and for the silicon it is 2.3 millivolt per degree centigrade rise in the temperature for the silicon. So these data are for the average characteristic of the diode. So if you will assume the value as 2.5 millivolt for the conservative design for both cases, this is for the both cases germanium and silicon, then it will be better. So we can say that the temperature, the voltage is going to vary, that is the voltage is going to decrease by 2.5 millivolt per degree centigrade rise in the temperature. So this is our conclusion for the voltage change, temperature change. And in the next lecture we will see theoretically, and we will prove graphically that how these things are, voltage and reverse saturation currents are going to vary with increasing the temperature. So friends, if you like this video, then you can subscribe my channel Technical Academy. Okay, thank you.